I'll just go through it. A simply support beam of span 9 meter is pre-stressed with parabolic cable. It's a parabolic cable which has maximum eccentricity of 200 mm at midspan and 35 mm at the support. Okay, for that I have written the figure. So at the midspan you can see the eccentricity is 200 mm. Okay, and at the support it is 35 mm. Okay, above the neutral axis. Then the beam is 250 by 500 mm in cross section. That also I have written here. Area of steel in the cable is 700 mm square. So in the given data I have written area of steel is equal to 700 mm square. Then initial pre-stress is also given. That also I have written initial pre-stress in the cable 1000 Newton per mm square. Then average the anchorage slip is 2 mm. Creep coefficient is given. Okay, shrinkage, strain, coefficient of friction, all the constants required to calculate different types of losses are given. Okay, so moving to the question, the wires have to be tensioned 2 at a time from one end to a value of F1. Okay, to a value of F1 so as to overcome frictional resistance, and then relax to a value of F2 so that immediately after anchorage an initial stress of 100,000 Newton per mm square would be obtained at the jagged and unjagged ends. Okay, please understand this sentence carefully. Here, relaxation for loss due to friction and loss due to anchorage slip is given, which means that the initially what will be the possible loss due to friction and possible loss due to the anchorage is calculated. Okay, and that loss is added to the initial pre-stresses so that the loss due to friction and anchorage will be overcome. Okay, so for example, if you are applying a pre-stress of around 1000 Newton per around 1500 Newton per mm square, okay, there will be loss due to friction and the anchorage. Okay, if you assume a loss due to friction and friction is as 50 Newton per mm square, loss due to anchorage is around 30 Newton per mm square, then remaining final free stress will be how much? This 50 is loss due to friction, 30 Newton per mm square is loss due to anchorage slip. Okay, so in out of 1500, what is the remaining stress? It will be 1420, correct? 1420 is the final stress after all the loss, after the loss due to friction and the anchorage. In this problem, what it says is the loss due to friction and the anchorage will be overcome. Okay. Okay, F1 so as to overcome frictional resistance. Okay, and loss due to anchorage. If you want to overcome loss due to frictional resistance and the anchorage, you must apply the initial stress including this loss due to friction and the anchorage. Okay, instead of applying initial stress of 1500, if you apply 1005, this 50 plus that is 80, 580 Newton per mm square, then you can overcome loss due to friction and the anchorage. That is what the question. Here, what he want is he want initial pre-stress after overcoming of loss due to friction and the anchorage to be as 1000 Newton per mm square. Okay, after overcoming loss due to friction and anchorage, the initial pre-stress should be how much? 1000 Newton per mm square. Okay, now what should be the initial pre-stress to be applied to overcome loss due to friction and the loss due to anchorage? Okay, to get the initial pre-stress of 1000 Newton per mm square. That is the question here. Here what we will be doing is, here what we have to do is, first we have to find loss due to friction. Okay, then whatever the value you get, no loss of stress due to friction, that stress should be added to the initial pre-stress. Okay, after that we will find loss due to friction. Loss due to friction. Okay, you will get some stress for loss due to friction. That stress should also be added to the initial pre-stress. So that if you apply that much initial pre-stress, which includes loss due to friction and the anchorage, then initial final stress after the losses due to friction and the anchorage will be this 1000 Newton per mm square. Okay, let me solve the problem. If we go on solving the problem, you will understand it clearly. I hope you got some idea to solve this particular problem. Initially, you find loss due to anchorage slip. Okay, loss due to anchorage slip. Loss due to anchorage slip. Okay. So we have the formula for calculating loss due to anchorage slip. Loss is equal to delta ES divided by L. Okay, delta ES by L. And anchorage slip value is given, it is 2 mm. Okay, Young's modulus of steel is also given. Length of the beam is also given. 9 meter span, it is 9 meter. Length of the beam is 9 meter. Now, loss due to anchorage slip will be equal to, loss is equal to 2 mm into Young's modulus of steel ES. Is it given? If it is not given, you know the value. Yes, 2 into 10 power 5, 210 gigapascal. ES is equal to given as 210 gigapascal, which is nothing but 210 into 10 power 9 Newton per meter square. If you want to get Newton per mm square, it will be 210 into 10 power 9 into 10 power minus 6 Newton per mm square. Finally, you will get it as 2.1 into 10 power 5 Newton per mm square. Sometimes it will be given. If it is not given, you are all familiar with this constant, 2.1 into 10 power 5 Newton per mm square. 2.1 into 10 power 5 divided by 9 meter is the span of the beam. In terms of mm, it is 9000 mm. By this, you will get loss due to anchorage slip. How much you will get? Check the answer. 46.67 Newton per mm square. 46.67 Newton per mm square. Okay. Now this loss due to anchorage slip is 46.67 Newton per mm square. To overcome this loss due to anchorage slip, what we have to do? We have to add this 46.67 to this initial pre-stress. Okay. Therefore, initial pre-stress F2 is equal to, therefore, F2 is equal to 1000 plus, here that F2 denotation notation is given here. Okay. For the final pre-stress after overcoming loss due to anchorage, 1000 plus 46.67, 46.67, you will get 1046.67 Newton per mm square. Okay, this is loss due to anchorage slip. Okay, if you apply a 1046.67 Newton per mm square as initial pre-stress, in that 46.67, if it goes for loss due to anchorage slip, only you will get the same initial pre-stress. That is, this initial pre-stress will be remained as 1000 only. That is the meaning. Okay. Similarly, now you calculate loss due to friction. Loss due to friction. You calculate now. So we know the formula. To overcome loss due to friction, again, so here you need to take, first you write the formula for loss due to friction. Loss due to friction is, what is the formula? P naught into mu alpha plus kx is the formula, correct? To calculate the loss due to friction. Now, Now the initial stress will be this one. Okay, 1046.67. Okay, so initial pre-stress is 1046.67. If you apply 1046.67 Newton per mm square, then loss due to anchorage slip will get overcome. Okay, now the initial pre-stress should be assumed as P naught is equal to initial pre-stress is taken as 1046.67 Newton per mm square. Okay, don't take 1000 Newton per mm square. Okay, 1046.67 you need to take as initial stress, then you need to calculate the friction, last due to friction. Again, for this 1046.67, whatever the last due to friction you get, that you need to add to overcome last due to friction and anchorage, last due to both friction and anchorage. Okay, and coefficient of friction mu, it is given in the problem. Coefficient of friction, it is 0.40, correct? 0.40, 0.40. Then what else you need? Wobble coefficient or wave effect constant, it is also given. K is equal to how much it is given? 0.15 per 100 meter. 0.15 per 100 meter. 100 meter. Okay. So 0.15 divided by 100 means 0.0015 per meter. Okay. So K becomes equal to 0.0015 per meter. Then what else you needed? You need the value of alpha and the x, no? You need the value of alpha and the x. Okay. First you calculate the slope. Okay. For parabolic cable. For parabolic cable. The type of cable given is parabolic, correct? It's a parabolic cable. The slope is calculated as 4e by L. Slope is calculated as 4e by L. Okay. So here 4 into, you should be very careful here. Eccentricity means it is the total eccentricity between top and bottom of the cable. Okay. See here above the neutral axis it is having an eccentricity of 35 mm. Below the neutral axis it is having an eccentricity of 200 mm. So here you need to consider the total eccentricity. Okay, you need to consider total eccentricity. So here it is 35, 200 plus 35 you need to substitute. Okay, while doing the calculation for last due to friction. Okay, in previous problems here eccentricity was 0. So whatever the eccentricity you get it at the middle of the span that you used to take. But here there is some eccentricity at the support and some eccentricity at the midspan. There is some eccentricity at the support above the neutral axis. There is eccentricity at the midspan below the neutral axis. So the total eccentricity is taken as 200 plus 35. You need to substitute total eccentricity here. So let me write here as 200 plus 35 divided by length of the beam 9 meter, 9000 millimeter. So for this you'll get 0.104. Okay, slope. Now you can calculate the alpha. Now you can calculate the alpha. So this alpha value depends on whether cable is pulled from one end or both the ends. Okay, whether the cable is pulled from one end or the both the ends. It depends on that thing. So here you go through the problem. Here it is clearly mentioned. Okay, the wires have to be tensioned to at a time from only one end. So if the cable is pulled from one end, formula for alpha is equal to 2 into slope. Okay, so in model beginning of the model I have given all the guidelines for calculating of this alpha and x here. Okay, you can refer to that. Okay, 2 into slope. So 2 into 0.104. If you do, you will get the answer as 0.208. Okay, and you need the value of x now. X is taken as L if the cable is pulled from one end. That too in meter. In meter, that is 9 meter. Okay, because cable pulled from one end. Cable pulled from one end. Okay, now you can calculate the loss due to friction. Therefore, loss is equal to P naught. P naught is 1046.67. 1046.67 into mu alpha plus kx. Mu is 0.4. Alpha is 0.208. 0.4 into 0.208 plus kx. K is 0.0015. 0.0015 into x is 9 meter. Okay, by this you'll get loss due to friction. Okay, please calculate the answer. If you calculate it, you will get the answer as 101.21 Newton per mm square. Please cross check the answers. Okay, now to overcome loss due to friction, the initial pre-stress. Okay, therefore now the initial pre-stress should be increased by initial pre-stress F2 should be increased by 101.21 Newton per mm square. Now initial stress at presently initial stress is how much? 1046.67. Therefore here 1046.67 plus 101.21. If you do, you can overcome loss due to friction and the anchorage slip. Okay, it will be, sorry, this is F1. Okay, F2 is the stress after overcoming loss due to anchorage slip. Okay, then F1 is the stress after overcoming the loss due to friction. F1 is equal to 1147.88 Newton per mm square. 1147.88 Newton per mm square. Okay, now next step is to calculate the remaining losses. Loss due to shrinkage, creep, okay, and loss due to relaxation. Okay, so in this problem, what is the difference is, he said that the loss due to friction and loss due to anchorage is overcome by applying suitable initial pre-stress. That is the meaning. Okay, that is the difference here. For that, what we have done, we have calculated loss due to anchorage slip, loss due to friction, and we have added to 1000. We got 1147.88 Newton per mm square as the initial pre-stress. Okay. Now in the next coming calculations, no, we have to consider initial pre-stress as this 1147.88 as the initial pre-stress only. Okay, you have to consider this 1147.88 as initial pre-stress in the next coming calculations. Okay, now loss due to shrinkage, you calculate loss due to shrinkage. Loss due to shrinkage. So what is the formula for loss due to shrinkage? Loss is equal to shrinkage strain into Young's modulus of steel. Correct? Huh? Shrinkage strain multiplied by Young's modulus of steel. Shrinkage strain is given that value in the problem. Just look into the value. Shrinkage strain of concrete is 1.5 into 10 power minus 4. Okay. Shrinkage strain is equal to shrinkage strain in concrete is equal to, it is given as 1.5 into 10 power minus 4. Okay, and Young's model of steel we know already. Therefore, loss is equal to 1.5 into ES 2.1 into 10 power 5. Okay, so answer is 31.5 Newton per mm square. Okay, so to this last due to shrinkage is over. What is the next losses? Loss due to creep is there, correct? Loss due to creep you can calculate. Okay, for that the creep coefficient is given, correct? What is the formula for calculating loss due to creep? Loss is equal to, what is the formula? Pi into Fc into m. Okay, and pi is nothing but creep coefficient that is given in the problem. Creep coefficient, creep coefficient, it is given as how much? Creep coefficient, here it is given 1.2, correct? Creep coefficient is given as 1.2. Let me take the value as 1.2. Then modular ratio, just check whether it is given or else we have to calculate. Modular ratio, yes, that it is also given. Modular ratio is given as 6. Let me take the value directly. Modular ratio is 6. Okay, then you need to calculate the value of Fc. What is Fc? Stress in concrete at the level of steel, correct? Stress in concrete at the level of steel. This we will calculate now. Calculation of Fc. Calculation of Fc. Okay, calculation of Fc. Okay, so it is a parabolic cable. Okay, type of cable is parabolic cable. So stress at the level of stress in concrete at the level of steel varies with the profile of the cable. If it is a straight, it would have been constant. It is a parabolic. So for that you need to find Fc at the support and Fc at the midspan. Then you can estimate average Fc. Okay, this we have practiced in the previous problems. Okay, so we know that. What is the formula? Fc is equal to P by A plus PE by I into E minus M by I into E. Okay. Now initial pre-stressing force. Okay. Pre-stressing force. Now you have to calculate it. Stress into area of cable. Area of cable. Initial pre-stress is how much? How much you have to assume? You have to assume initial pre-stress of 1147.88 Newton per mm square. Okay, because loss due to friction and the loss due to anchorage, okay, are overcome by increasing this initial pre-stress. Correct. So initial pre-stress we need to assume as 1147.88 now. So it is 1147.88. 1147.88 into area of cable. It is also given in the problem. Area of the cable, area of steel in the cable is 700 mm square. So here in the given data written. Okay, it is 700 into 700. If you do, we will get initial pre-stressing force. Okay, please calculate the answer. It is 803.52 into 10 power 3 Newton. Okay, in terms of kilonewton, it is 803.52 kilonewton. Okay, now you got the P, then area of cross section A is equal to, the sectional dimensions are given. What are the sectional dimensions given? 250 by 300. Okay. Area of cross section. Area of cross section A is equal to, it's given as 250 by 300. So 250 by 300 or 500 it is. So yes, it is 250 by 500. So here, let me correct it here. 500. So 250 by 500. 500. By this you'll get area of cross section as 125 into 10 power 3 mm square. Okay. Now you got the cross sectional area. Then you need moment of inertia I. I is equal to VD cube by 12. So B is 250 into 500 cubes by 12. Okay. The answer is 2.604 into 10 power 9 mm 4. Okay. Now moment of inertia you got. Then this moment is also required, but here loading condition on the beam is not given. Loading condition on the beam is not given. Live load on the beam is not given. Therefore, we will ignore this moment effect. Okay, we will assume moment as 0. Okay, because live load not given and dead load moment is neglected. Okay, in the absence of live load moment, we have to take this m value as 0. Okay, now you got P, you got the value of A, and moment of inertia is also known. Eccentricity at support and midspan are known. Now you can calculate FC at support and FC at midspan. Okay, let me write the values here. Here at the support, eccentricity is minus 35 mm at support. Okay, here this is at midspan. At midspan, eccentricity is 200 mm. Okay, why it is minus 35? It is above the neutral axis. If the cable goes above the neutral axis with some eccentricity, that eccentricity is denoted by negative sign minus 35. Okay, so below the neutral axis plus 30 plus value. Okay, you need to use the positive value. Okay, therefore at support, eccentricity corresponding eccentricity is minus 35 mm. Okay, at support eccentricity is minus 35 mm. Now I can calculate FC support. Therefore FC support P by A. P is 803.52 into 10 power 3. 803.52 into 10 power 3 divided by area of cross section 125 into 10 power 3. Okay, plus PE by I into E. 803.52 into 10 power 3 into E support is minus 35 divided by I is 2.604 into 10 power 9 into minus 35. Okay. So by this we'll get stress in the concrete at the level of steel at support. FC support is equal to, it is 6.80 Newton per mm square. 6.80 Newton per mm square. Okay. Similarly, you calculate the FC at midspan. At midspan, okay, the eccentricity corresponding eccentricity is how much? At midspan it is 200 mm. 200 mm. Okay, E midspan is equal to 200 mm. Therefore, FC midspan is equal to P by A. P by A same value 803.52 into 10 power 3. 803.52 into 10 power 3 divided by 125 into 10 power 3 plus PE by I into E. 803.52 into 10 power 3. Eccentricity at midspan is 200 divided by 2.604 into 10 power 9 into eccentricity 200. By this we'll get stress in the concrete at the level of steel at midspan. FC midspan is equal to, you will get it as 18.77 Newton per mm square. 18.77 Newton per mm square. Now you can calculate by utilizing this FC at support and FC at the midspan. You can calculate the average FC. Okay, at support it is 6.8. At support it is 6.8, and at midspan it is 18.77. Okay, so up to here average stress is 6.8. Okay, therefore average FC is equal to, see, from here to here average stress is 6.8 plus, now you have to convert this parabola into a regular rectangle, means you need to convert this parabolic variation of the stress into a uniform stress variation. Okay, so how to convert? So this length, so this is total is 18.77. So this length will be 18.77 minus 18.77 minus 6.8. Okay, this height. Okay, so two-third of height at the left side plus height on the right side. Height at the left side is 0 and on the right side is 18.77 minus 6.8. Correct? So two-third of 18.77 minus 6.8. Okay. So you can directly calculate this average FC without writing the diagram. You remember like this: smaller value plus two-third of larger value minus smaller value. Okay. Smaller FC value is 6.8 plus two-third of larger minus smaller. If you do, you'll get the average FC. Okay. So average FC, if you calculate, you'll get it as 14.78 Newton per mm square. 14.78 Newton per mm square means you have converted this parabolic variation into a uniform variation. Okay, having the constant stress distribution of 14.78 Newton per mm square throughout the length. Okay, so this is how we calculate average FC. Okay. Now you got average FC. Therefore, the loss is, we have the formula that is pi into FC TM. Pi is 1.2, M is 6, FC just now we have calculated, that is 14.78. Therefore, the loss is equal to, therefore, the loss is equal to 1.2 into 14.78 into 6 is equal to, you will get the answer as 106.42 Newton per mm square. Okay. Now you have calculated loss due to creep and loss due to shrinkage. So last one more type of loss is remaining, that is loss due to relaxation. Last one, loss due to relaxation. relaxation. Okay, so percentage of relaxation of stress in the steel is given in the problem. It's given as 2% of the initial stress. Okay, so initial stress is 1147.88 Newton per mm square. Below, right? Percentage relaxation of stress in steel. Percentage of relaxation of stress in steel is given as 2%. Therefore, loss is equal to 2 by 100 into initial stress 1147.88. By this percentage relaxation, so loss due to relaxation of stress in steel. Take the answer. It is 22.95 Newton per mm square. Okay. So to this, this problem is over. If you have got any doubts at any point of calculation, you can ask students. Any doubts here in this problem? Any doubts?
Sir.
Yes. Okay. Thank you. With this, we'll move on to the next problem. That is problem number 7. So this problem number 7, you take it as homework. Okay. It is similar to the previous problems. Okay. Similar to the previous problems. There is some minor difference. I will explain. Okay. Problem number 7. You solve by yourself. Try to solve by yourself. If you get any doubts, you can come to me. Okay. Okay. Here I have solved already. A pre-tensioned beam 200 mm wide, 300 mm deep is pre-stressed by 10 wires of 7 mm diameter. Okay, there are 10 wires. Okay, and each wire is having 7 mm diameter. Initial stress to 1200 Newton per mm square with their centroids located 100 mm from soffit. Okay, here I have written the figure. Okay, the cables are located 100 mm from soffit. Here I mentioned that. Okay, center of the cable is located 100 mm from soffit of the beam. Okay, find the maximum stress in concrete immediately after transfer, allowing only for elastic shortening of concrete. Allowing only for elastic shortening of concrete. If the concrete undergoes a further shortening due to creeps and shrinkage, while there is relaxation of 5% of stress in steel, estimate the final percentage of loss of stress in the wires using IS code. Okay, and all the data required is given here. Here at the beginning, what it says is find the maximum stress in concrete immediately after transfer, allowing, okay, allowing only for elastic shortening of concrete. Means what you have to do now for the calculation, you need to take initial pre-stress, okay, as initial pre-stress as the pre-stress, okay, minus loss due to elastic shortening as the initial pre-stress. Okay, he says that allowing loss due to elastic shortening. Okay, he said to allow the loss due to elastic shortening means first you need to calculate loss due to elastic shortening. Okay, whatever that value we get now, here I calculated that. Okay, loss due to elastic shortening, elastic deformation I have calculated. Okay, in the problem he says that to allow the loss due to elastic shortening, allow the loss due to elastic shortening means the initial stress should be deducted. Okay, in the initial stress, this loss due to elastic deformation should be deducted. That is 100 to 1200 minus 58.5. This has taken as initial pre-stress for further calculations here. For further calculations here. Okay. So when he says allow, okay, allowing only for loss due to elastic shortening, then initially what you do, you calculate loss due to elastic shortening. Okay. And initial pre-stress applied is 1200 Newton per mm square. Okay. Here it is given 1000 Newton, 200 Newton per mm square. So out of this 1200, you calculate the loss due to elastic shortening. Okay. Loss due to elastic shortening, we got it as 58.5 Newton per mm square. Okay. Next, for the next coming calculations, okay, you need to take initial pre-stress as 1200 minus 58.5 as the initial pre-stress. Okay, as initial pre-stress for the next coming calculation means for calculation of next coming losses here. That is the meaning. Okay, here Young's models of steel is given, Young's models of concrete is given. Okay, and FCU value is given, coefficient of friction is given. Okay, shrinkage strain is given. Cross sectional area is given as 200 by 300. Okay, 200 by 300, and I have calculated the total area. And Young's models of concrete, he has given 5700 root of FCU. FCU value is also given. Just substitute the value of FCU. I got it. I got this value. I got this value. Okay. Then moment of inertia I have calculated. Modular ratio is nothing but the ratio of Young's modulus of steel and the concrete. That also I calculated. I got it as 5.7. Okay. Now the initial stress in the steel is given as 1200 Newton per mm square, and he says that the wire is comprising of 7 mm dia and 10 numbers. Okay. So this initial stress multiplied by area of the steel will give initial pre-stressing force. Correct. Therefore, what I have done, 1200 is the initial pre-stress into total area of wire. He says that there is 10 number of 7 mm dia bars. Okay. So pi d square by 4 into 10 numbers will give total area of steel. Total area of steel multiplied by stress in the steel 1200 will give initial pre-stressing force in the steel. Okay, initial pre-stressing force in the steel. So next, to calculate loss due to elastic deformation M into FC. FC I have calculated. Okay, FC I have calculated. Initial pre-stressing force is 461.81 into 10 power 3 Newton. Area of cross section here I have calculated. Okay, then moment of inertia also calculated, and eccentricity is constant throughout the length. Okay, so the sectional dimension is, it is 200 mm wide, 300 mm deep. Okay, total depth of the beam is 300. Okay, so central axis becomes half of 300, 150. So 150 minus this 100 will give this eccentricity. Okay, so eccentricity will be 50 here. Okay, 50. That calculation I have done here in the diagram only. 50 eccentricity is equal to 50 mm. Okay. Now eccentricity I have substituted 50. Finally, I got the FC value. Okay. Therefore, loss due to elastic deformation is M into FC, modular ratio into FC. I got this loss due to elastic deformation. Okay. Now he says that allow the loss due to elastic deformation. Allow the loss due to elastic deformation means that you need to deduct this loss in the initial pre-stress. 1200 minus 1200 is the initial pre-stress. In that, loss due to elastic deformation is 58.5. Sorry students, it was an office call. We'll resume the class. So after getting loss due to elastic deformation, you need to deduct that loss due to elastic deformation in the initial stress. 1200 minus 58.5. If you deduct, you will get the initial pre-stress into multiplied by again area of cable will give initial pre-stressing force. Okay, initial pre-stressing force after allowing loss due to elastic deformation. Okay, that is 439.3 into 10 power 3 Newton. Okay. Now in the for the next coming calculations, now you need to take initial pre-stressing force as this one, not the 500. Okay, initial pre-stressing force, how much we have here? Is 1200 into is 461.81 into 10 power 3 Newton is there, no? This you should not consider for the further calculations. Okay, you need to take 431.3 into 10 power 3 Newton. He says that allow the loss of stress due to elastic deformation. After allowing this initial pre-stressing is reduced to 439.3 into 10 power 3 Newton from 461. Okay, so for the next coming calculations, you need to take this as initial pre-stressing force P. Okay, so when you reduce this, when you take this, when you assume this 439.3 into 10 power 3 Newton as the initial pre-stressing force, then FC value will change. Then FC value will change. Okay, in place of 461.81, what will come? 439.3 into 10 power 3 value will come. So this is a modified value of FC. So for future calculations, this FC value is taken to do the to calculate the remaining losses. Okay. Now other losses have been calculated. Loss due to elastic deformation is 58.5 Newton per mm square. That this we have already calculated here at the beginning, 58.5. Then loss due to creep is equal to pi into FC into M. Pi is given as 1.6. FC, how much you have to take? 9.76, not the top one, not this 10.26, 9.76 you need to take as FC, modified FC. And modular ratio is also given 5.7. Okay. And due to shrinkage, calculated relaxation of stress, it is also calculated. Finally, total loss is calculated. Okay, total loss is calculated. Then final stress after the loss will be initial stress is 1200. In that 270 is the loss. 1200 minus 270 will give 929.5 Newton per mm square. Percentage loss of stress is also calculated. Total loss in is 270 out of 1200 into 100 will give percentage of loss. Okay. So please solve yourself in the home. If you get if you get any doubt, you can come to me anytime. Okay. Now I'll move on to the problem number 8. Problem number 8. All of you read this problem. This is problem on concrete pile. Okay, this is the problem on concrete pile. Write it. All of you read the problem. Okay, so here go through it. A pre-stressed concrete pile. Okay, having 250 by 250 mm square, area of cross section is given. Solution. Area of cross section A is equal to 250 by 250 mm square. So if you multiply, it will be 625. Okay, 62,500 mm square. Okay, this is the cross sectional area. Contains 60 pre-tensioned wires, each of 2 mm diameter. Okay, there are 60 number of wires and each wire is having diameter of 2 mm. 2 mm uniformly distributed over the section. Okay, it's a concrete pile. Okay, in this, what is there? 60 number of pre-stressing wires are there. Okay, 60 number of pre-stressing wires are there, and each wire is of 2 mm diameter. Okay, 60 numbers, 2 mm each diameter, uniformly distributed over the section. The wires are initially tensioned, okay, on the pre-stressing bed with a total force of 300 kilonewton. Initial pre-stressing force is given. Pre-stressing force. Pre-stressing force is given as 300 kilonewton. P, which is nothing but P. 300 kilonewton or 300 into 10 power 3 Newton. Okay. Then calculate the final stress in concrete and percentage loss of stress in steel after all losses. Okay, Young's models of steel concrete is given. Shrinkage shortening due to creep is given. Then shrinkage strain is given. Relaxation of stress in steel is given. Initial pre-stressing force is given as 300 kilonewton. Okay. Now you need to calculate all the losses, then total loss and percentage of loss. Okay. Now you calculate the basic parameters required for calculation of the losses. What are the basic parameters required? You need the value of area of concrete pre-stressing force. You need the value of FC. You need the value of modular ratio. Correct. All those things you calculate first. Modular ratio calculate. Modular ratio M is equal to ES by EC. Young's modulus of steel is 210 by 32. 210 by 32. You will get it as 6.57 modular ratio. Okay. Then initial pre-stress in steel wires. You can calculate initial pre-stress in wires. In wires is equal to initial pre-stressing force divided by area of steel. Okay, initial pre-stressing force is given as 300 kilonewton. 300 into 10 power 3 Newton divided by area of steel. Okay, for area of steel, he says that there are 60 number of wires, each having 2 mm diameter. So area of 1 bar will be equal to pi d square by 4, pi into 2 square by 4 into 60 numbers. Okay, by this we will get initial pre-stress as 1591.54 Newton per mm square as initial pre-stress. Okay. Then stress in concrete at the level of steel. Okay. Then stress in concrete at the level of steel. FC is equal to stress in concrete at the level of steel is equal to, as this is a column or the pillar, FC is calculated as directly load by area, P by A. P by cross-sectional area A. Okay, so P is 300 into 10 power 3 divided by cross-sectional area is 52,500. 62,500. Okay, so how much you'll get? 4.8 Newton per mm square FC. Okay, FC will be equal to, this is FC. Okay, the actual formula is what? FC is equal to P by A plus PE by I into E plus M by what is that? M by I into plus M by I into E. No, let me check it. M by I into E minus M by I into E minus M by I into E. Okay, this eccentricity is 0 here. Okay, there is no eccentricity because all the cables are distributed equally throughout the cross section. There is no eccentricity. It is considered as 0. So eccentricity is 0. These two terms become 0. Okay, only you will get P by A FC. Okay, P by A. Okay. Now we can calculate all the losses. Write the sided line as losses of stresses. Okay. So we calculate one by one. First one is loss due to elastic deformation. Elastic deformation is equal to, what is the formula? M into FC. Modular ratio is known 5 point. How much it is? 6.57. 6.57 into FC is 4.8. Okay. So you will get it as 31.5 Newton per mm square. So by this you will get loss of stress due to elastic deformation. Second one is loss due to creep of concrete. So we have the formula that is epsilon CS into FC into ES. Okay, this epsilon CS is given here. Shortening due to creep 30 into 10 power minus 6. 30 into 10 power minus 6 into FC is 4.8 into Young's modulus of steel 210 into 10 power 3. Okay, 210 kilonewton means 210 into 10 power 3 Newton per mm square. 210 into 10 power 3. So by this we'll get loss due to creep, that is 30.24 Newton per mm square. Okay. Next, third one, loss due to shrinkage of concrete. Loss due to shrinkage of concrete is equal to, loss due to shrinkage of concrete is equal to, formula we have is epsilon CS into ES, where epsilon CS is shrinkage strain in concrete. Okay, in this it is creep coefficient. Okay, shrinkage strain in concrete is given 200 into 10 power minus 6, that is 200 into 10 power minus 6 into 210 into 10 power 3. If we calculate, it is 42 Newton per mm square. Then finally, relaxation of stress in steel is also given. It is given as how much? 5%. For 5%, we calculate the loss of stress, relaxation of stress, relaxation of stress in steel is equal to, it is given as 5 by 100, 5%, 5 by 100 of initial pre-stress. How much? 1591.54. So by this we'll get the answer as 79.57 Newton per mm square. Okay. Therefore, the total loss we can work out sum of all the values it is 183.28 Newton per mm square. Okay. Total loss of pre-stress is 183.28 Newton per mm square. So after considering the losses, the effective pre-stress will be equal to initial stress is 1591.54 Newton per mm square. 1591.54 Newton per mm square. In that there is 183.28 is the loss. Therefore the effective pre-stress is 1408.26 Newton per mm square. Okay. This is the effective pre-stress that exists in the member. Okay. So in the question, you just go to the question. What is the question here? Calculate the final stress in concrete. Okay. Calculate final stress in concrete. Okay. Now effective pre-stress after considering all the losses is 1408.26 Newton per mm square. Okay. Therefore effective pre-stressing force force is equal to effective pre-stress into area of the cable. Okay. Effective pre-stress into stress into area of cable. Okay. Area stress is 1408.26 into area of cable is pi into there are 60 number of cables having diameter of 2 mm into 60. Okay, diameter of one bar is pi d square by 4, pi into 2 square by 4 into multiplied by 60 will give the effective pre-stressing force. Okay, this is a force P. Okay. What is the question? Question is to calculate final stress in concrete. Final stress in concrete. Now you got effective pre-stressing force. Okay. Therefore, final stress in concrete is equal to final pre-stress in concrete is equal to E by A. Effective pre-stressing force divided by area of concrete. The same term I will write here. If you want, you can calculate and directly put the answer. 1408.26 into pi into 2 square by 4 into 60 whole divided by area of concrete. It is how much? 62,500. 62,500. By this, you'll get the answer. The final pre-stress in the concrete. You will get it as 4.25 Newton per mm square. Okay. If you want, you can calculate percentage loss of stress also. Percentage loss of stress as well. So total loss is how much? Total loss is 183.28. There is 183.28 Newton per mm square loss out of how much? Out of 1591.54. 1591.54 into 100. By this we'll get percentage of loss. We'll get it as 11.51%. Okay. So to this problem is over. Okay. The final stress in concrete we have calculated. Percentage loss of stress is also we have calculated in the last step here. We got it as 11.51%. Okay. So to this problem is over. Any doubts you can ask. Any doubts you can ask students. Okay. We move on to the next problem. Problem number 9. Please write this problem. All right, write this problem. Elaborate this problem. I hope you are writing this problem number 9. You go through it. A pre-stressed concrete beam 200 mm wide and 300 mm deep is pre-stressed with wires. Okay, having area of 320 mm square located. Okay, below I'll write given data one by one. Solution. Okay, a pre-stressed concrete beam of 200 by 300 mm wide. Okay, area of cross section is given. Area is equal to 200 by 300, that is 60,000 mm square, and area of wires is given 320 mm square. Area of wires is given as 320 mm square, located at a constant eccentricity of 50 mm. Eccentricity is given, E is equal to 50 mm, and carrying initial stress of 1000 Newton per mm square. Initial stress is given. Initial stress P naught is equal to 1000 Newton per mm square. Okay, 1000 Newton per mm square. Then the span of the beam is 10 meter. The span of the beam is given. Length of the beam, it is given as 10 meter. Span of the beam is 10 meter. Calculate the percentage loss of stress in wires. Okay, if the beam is post tensioned using the following data. Okay, ES is equal to, here we add one more thing here. Beam is post tensioned. Here first one is post tensioned and one more is pre-tensioned also. Okay, he has given the values with respect to post tensioning as well as pre-tensioning using the following data. Okay, Young's modulus of steel, concrete is given, relaxation of stress in steel. Okay, shrinkage coefficient, creep coefficient. Okay, see, he has given the shrinkage of concrete for pre-tensioning is 300 into 10 power minus 6, and for post-tensioning 200 into 10 power minus 6, which means that we have to do individual calculations for both the cases. When the beam is pre-tensioned, what will be the loss? When the beam is post-tensioned, what will be the loss? For both cases, we have to perform the calculations. Creep coefficient is given, slip of anchorage is given, and frictional coefficient is also given. Okay. Now, let me write the given data in detail. ES is equal to 210 kilonewton per mm square. ES is equal to 210 kilonewton per mm square, which is nothing but 210 into 10 power 3 Newton per mm square. Then EC is equal to, how much it is given? EC 35 kilonewton per mm square. 35 kilonewton per mm square is equal to 35 into 10 power 3 Newton per mm square. Okay. Relaxation of stress in steel is given. Relaxation of stress in steel is equal to, it is given as 5%. Then shrinkage of concrete for is 300 into 10 power minus 6 for pre-tensioning and 200 into 10 power minus 6 for post-tensioning. With respect to shrinkage stress calculation, the epsilon CS value is 300 into 10 power minus 6 for pre-tensioning. And it is 200 into 10 power minus 6 for post-tensioning. 200 into 10 power minus 6 for post-tensioning. Okay, then creep coefficient is given pi 1.6, 1.6. Then anchorage slip is given as 1 mm. Delta is equal to 1 mm. Then coefficient of friction. Frictional coefficient for wave effect. Okay, wave effect means K 0.0015 per meter. K is equal to 0.0015 per meter. Okay, these are all the values given. Okay, now you have to calculate all the relevant losses. Before going to calculate all the losses, you calculate the basic parameters. What are the basic parameters needed? Pre-stressing force P is needed, modular ratio is needed, moment of inertia is needed. Okay, FC value is needed. All these values first you calculate, then you can calculate all the different losses individually, and you can calculate the total loss. Okay, so first you calculate the pre-stressing force. Pre-stressing force P is equal to stress in the wires is given. Initial pre-stress, how much it is given? It is given as 1000 Newton per mm square P naught. Okay, initial pre-stress multiplied by area of wire will give pre-stressing force. Initial pre-stressing force. Stress into area of wire. Initial pre-stress is 1000 Newton per mm square. Area of wire is given as 320 mm square. By this we'll get pre-stressing force. Okay, so we'll get it as 320 into 10 power 3 Newton or 320 kilonewton. Okay, now you got pre-stressing force. Then you find modular ratio. Modular ratio is equal to M is equal to ES by EC. Young's modulus of steel to that of Young's modulus of concrete. ES is given and EC is also given. ES is 210, EC is 35. Therefore, 210 by 35 you will get 6 as modular ratio. Okay, then you find moment of inertia. I is equal to BDQ by 12. So these are all basic parameters which are needed for every calculations for every problem. Okay, I is equal to BDQ by 12. B is given as 200 and the depth is given as 300. 200 by 300 cube by 12. 200 into 300 cube by 12. So by this we get moment of inertia as 450 into 10 power 6 mm4. Okay, then you calculate the FC. For the formula for FC is P by A plus PE by I into E minus M by I into E. Okay, so in this the loading condition on the beam is not given. Plane load on the beam is not given. Therefore, moment will assume it as 0. Okay, moment we will assume it as 0 because there is no loading condition given. Okay, therefore P precessing force just before we have calculated, that is 320 to 10 power 3 Newton. Area of cross section also we have calculated. Okay, area of cross section is 60,000 mm square, and eccentricity is given in the problem directly. It is given as 50 mm. Okay, it is having constant eccentricity. It is not a parabolic cable. It is a straight cable. Okay, he says that constant eccentricity. Constant eccentricity when it will come, when the cable is straight, then only you will get constant eccentricity. Okay, so if it is a parabolic cable, you would have calculated the FC at support, FC at midspan, you would have calculated average FC. But here the eccentricity is constant throughout the length of the beam. So with respect to this eccentricity, if you calculate the FC, that will itself the average FC only. Okay, therefore FC is equal to P by A. P is pre-stressing force 320 into 10 power 3 into 10 power 3 divided by area of cross section. Area of cross section 60,000 plus PE by I 320 into 10 power 3 divided by moment of inertia 450 into 10 power 6 into E is 50 and 50. 50 and 50. So by this we'll get FC. So we'll get the answer as 7.11 Newton per mm square. 7.11 Newton per mm square. Okay. So to this we have calculated all the basic parameters required for calculating the different losses. Now you can calculate all the losses. Okay. So here there are both the pre-tensioning and post-tensioning conditions are given. As I said before, you need to calculate the losses individually. For pre-tensioning and post-tensioning separately you need to calculate, and you have to add up all to get what is the percentage of loss or total loss for pre-tensioning case and what is the total loss for post-tensioning case. Okay, now you make a tabular column. Make a tabular column. In the first column, type of loss you write. Type of loss. In the second column, you write pre-tensioned beam. Pre-tensioned beam. In the third column, post-tensioned beam. Okay. Now we will calculate each and every losses one by one for each type of beam. Okay. What is the first loss? We come across elastic deformation loss due to elastic deformation. Loss due to elastic deformation. What is the formula for calculating loss due to elastic deformation? It is M into FC. Correct? Huh? Okay. M into FC. M into FC. Loss is equal to M into FC. Okay. Therefore, M is calculated before modular ratio. We got it as how much? Modular ratio. We got it as 6. M is 6 into FC 7.11. 7.11. By this we'll get total loss as 42.66 Newton per mm square. Okay. Then what about loss due to elastic deformation in post-tension beam? Whether it will be there or not. It depends on whether the cable is pulled simultaneously or one by one. Here you can see that pre-stressed with wires located at a constant eccentricity of 50 mm and carrying initial stress. Okay, here it is not mentioned whether the cables are pulled simultaneously or one by one. Okay, if it is not mentioned, it is by default it is understood that the cables are pulled simultaneously. Okay, if the cables are pulled simultaneously, there will not be any loss due to elastic deformation for post tension beam. So this will not come. Okay. Particularly if it is mentioned like the cables are pulled one by one, then only you need to calculate loss due to elastic deformation for post tension beam. Otherwise, you have to assume that the cables are pulled simultaneously and it is zero. Okay, to this the loss due to elastic deformation is over. Okay, next second type of loss is loss due to relaxation of stress in steel. Relaxation of stress in steel. Okay, and percentage of relaxation of stress is given in the data. How much it is given? 5%. Okay, 5% of the initial stress. Initial stress is 1000 here. So 5% of 1000 loss is equal to 5% of 1000. 5% means 5 by 100 into 1000. Okay, so you will get 50 Newton per mm square. Okay, and loss due to relaxation of stress in steel will be there in both pre-tension and post-tension beam. It will be there for pre-tension and post-tension beam. So here we will get the same calculation. You will get the same answer, 50 Newton per mm square. Okay, to this loss due to relaxation of stress in steel is calculated. Next, coming to the next loss. Okay, due to creep of concrete. Loss due to creep of concrete. Okay, loss is equal to, we have the formula pi into fc into m. Pi into fc into m. So creep coefficient is given with respect to creep. Pi is given as 1.6. fc is known, m is 6. Substitute 1.6 into fc is 7.11 into 6. By this we get loss due to creep. Okay, you will get it as 68.26 Newton per mm square. And for post tension beam also, loss due to creep will be there. Okay, long term loss. Okay, time dependent loss. It will be there for both the cases. Okay, you will get the same answer here also. Okay, loss is equal to, you will get the same answer, 68.26 Newton per mm square. Okay, to this loss due to creep is calculated. Next, we will go for next type of loss, that is loss due to shrinkage. Shrinkage loss. Okay, we'll calculate the shrinkage loss. See, very important with respect to shrinkage loss calculation, he has given two different constants. Okay, shrinkage coefficient, he has given two different constants for both pre-tensioning and post-tensioning. Here answer will not be the same. You need to do individual calculations. Okay, epsilon CS for pre-tensioning is 300 into 10 power minus 6. Epsilon CS for post-tensioning is 200 into 10 power minus 6. Okay, therefore loss due to shrinkage of concrete is equal to loss is equal to epsilon CS into ES. ES is 210 into 10 power 3 See, for pre-tensioning, what is the constant value? It is 300 into 10 power minus 6. Let me substitute 300 into 10 power minus 6 into 2 into 10 power 5. Okay, by this we'll get loss due to shrinkage as 63. Here loss is equal to CS into ES is equal to, here ES epsilon CS value is different for post tension member. It is given as 200 into 10 power minus 6. Okay, so 200 into, if it is same, we would have got same values. 10 power minus 6 into 2 into 210 into 10 power 3 or 2 into 10. Let me write the here value 210 into 10 power 3. Okay, by this we will get the loss as 42 Newton per mm square. Okay, then what are the remaining losses? We have till now we have calculated 4 different losses. 2 more are remaining. What are they? Loss due to friction is there, loss due to anchor slip is there. No, both we will calculate. Now fifth one, loss due to anchorage slip. Okay, and with respect to loss due to anchorage slip, it will be there only in case of post tension member, not in pre-tension member. Okay, it will not be there. Loss due to anchorage slip, because we are not going to provide anchors for pre-tensioned case. We are going to provide anchorages for only post tensioning cases. There you will get anchorage slip. Okay, so amount of slip is given. How much it is given? Delta. It is given as 1 mm. Okay, the formula is what? Anchorage slip loss due to anchorage slip is delta by L into ES. This is the formula. Delta is 1 mm out of total length of beam is how much it is given? Total length of the beam. Length of the beam. Just see where it is given. 10 meter. Yes, it is given as 10 meter. 1 mm divided by 10 meter is 10,000 mm. 10 into 10 power 3 mm into ES 210 into 10 power 3. By this we'll get loss due to anchorage slip. Okay. So you will get it as 21 Newton per mm square. Okay. To this loss due to anchorage slip is calculated. The last one remaining is loss due to friction. Okay. And with respect to loss due to friction, it will not be there in case of pre-tension members. Okay. Because there is no ducts here. Okay. Due to friction only, there will be prestresses induced into the concrete. Okay, it is not considered as loss here in case of pre-tension member. Only for post-tension member, this loss due to friction will come into picture. Okay, for that we have the formula. Loss is equal to P naught into mu alpha plus Kx. Mu alpha plus Kx. Okay, and P naught initial pre-stress is 1000 Newton per mm square. Okay, and this alpha is there, no? This alpha will be 0 for straight cable. For straight cable, why it is 0 means? Okay, let me go to the calculation part of alpha. See, for calculating alpha, you need the value of slope here, correct? Huh? You need the value of slope. Okay, if it is a straight cable, this slope becomes 0. the slope becomes 0. When slope becomes 0, alpha becomes 0. Okay, so for straight cable, the alpha value is 0. Okay, and K is equal to, it is given as how much? K is equal to 0.0015 per meter. 0.0015 per meter. Okay, and X is nothing but the length of the beam. It is 10 meter. In terms of meter, you need to substitute. Okay, therefore loss is equal to P naught is 1000 into mu alpha. Alpha, as alpha value is 0, so mu alpha value becomes 0 plus K into X 0.0015 into 10 meter. By this we'll get loss as 15 Newton per mm square. Okay, to this calculation of all the losses is over. Calculation of all the losses is over. Okay, now we can calculate total loss with respect to pre-tensioning and total loss with respect to post-tensioning. Okay, so here total loss of stresses, total loss of stresses is for pre-tensioned beam, it is 42.66 plus 50 plus 68.26 plus 63. If you calculate, you will get the answer as 223.92 Newton per mm square. Okay, for post-tension beam, it is 15 plus 21 plus 42 plus 68.26 plus 50. Okay, so it will be 196.26 Newton per mm square. Okay, if you know the total loss, you can calculate the percentage of loss. Okay, you can calculate the percentage of loss. Okay, you can calculate the percentage of loss now. Okay. Now percentage of loss will be equal to percentage of loss is equal to, see, for pre-tension beam, there is total loss of 223.92 Newton per mm square out of 1000 newtons into 100. If you do, you will get percentage of loss, that is 22.4%. Okay. Similarly, for post-tension beam, there is a loss of 196.26 Newton per mm square out of 1000. So into 100, if you multiply, you will get a percentage of loss as 19.62%. Okay, so to this, the problem is over. So here it is a quite different problem. Different means he has given for both pre-tension and post-tension beam. Okay, and when it is given like that, you need to do the individual calculations with respect to pre-tension beam and post-tension beam. Okay, and it's a very simple problem. Any doubts here in this problem? Do you need any clarification in this problem, students? I hope this is clear for everyone. Okay. So this will stop the class, and in the next session. So to this, one part of the model is over, students. Okay, calculation of losses of prestresses. Okay, one part is over. There is one more part in this model. Okay, there is one more part, that is calculation of deflection of a pre-stressed concrete member. Okay, this is one more part of the model. This we will discuss in the next coming class. Okay, to this we'll end the class. Thank you.